Now that we have seen the key geometric idea behind the ellipsoid method, we're ready to see how this algorithm can solve the linear programming feasibility problem. Once again, in the linear programming feasibility problem, we are given a polyhedron P in Rn, described by a system of linear inequalities Ax greater than or equal to b. Our task is to understand if this polyhedron is empty or not. To simplify the presentation and the analysis of the ellipsoid method, we start by making few assumptions. And to make these assumptions, I need to formally define what is a full-dimensional polyhedron. We say that the polyhedron is full-dimensional if it has positive volume. Note that in this course we have never defined the volume of a set. I am sure that you all have a very clear intuition of what the volume is, and this intuition will be enough for what we will see in this chapter. However, if you want to see the formal definition of volume, I refer you to the textbook. In any case, now I give you a couple of characterizations of full-dimensional polyhedra. The first one is that a polyhedron P in Rn is full-dimensional if and only if it contains n plus 1 affinely independent points. Another equivalent definition is that a polyhedron P is full-dimensional if and only if it contains a ball with positive radius. Now we are ready to state the two assumptions that we now make and that we will relax later. The first one is that the polyhedron is bounded, which means that it is contained in a box big enough. The second assumption is that the polyhedron P is either empty or full-dimensional. Our boundedness assumption immediately implies that there exists a ball that we call E0 that contains our polyhedron P. We denote by x0 the center of this ball and by r its radius. This assumption is clearly very useful to us because we know that the ellipsoid method, in order to start, needs an ellipsoid that contains P. Note that our ball E0 has positive volume, and we denote it by capital V. Let's now discuss assumption 2. It requires that either P is empty or P has positive volume. Saying that P has positive volume means that the volume of P is strictly larger than V for some positive V. From now on, we assume that we know the ellipsoid E0 as well as the number V and capital V. Later on, we're going to discuss how we can obtain them. Now, under all our assumptions, we can state the ellipsoid method, and we can show that it decides correctly if P is empty or not. Let's start by discussing the input of our algorithm. We have a matrix A and a vector B that define the polyhedron P, which is the set of X in Rn, such that AI transpose X greater than or equal to Bi for every I from 1 to m. In input, we also have a number V such that either P is empty or the volume of P is strictly larger than V. Finally, in input, we have a ball E0 with center x0 and radius r, with volume at most capital V, such that P is contained in E0. The output of our ellipsoid method is a feasible point x star in P if P is non-empty, or a statement that P is empty. In particular, note that the ellipsoid method, if P is non-empty, doesn't only give you a statement that P is non-empty, but it also gives you a feasible point in the polyhedron. Now let's see the algorithm. In the initialization step, we let T star to be the ceiling of 2n plus 1 log capital V over V. The number T star essentially will be the number of iterations that the ellipsoid method requires. Then we set E0 to be equal to the ball that contains P, and we set T equal to 0. In the algorithm, T will be the iteration counter. Now let's see the main iteration of the ellipsoid method. If T is equal to T star, it means that we have reached the last iteration, and so the algorithm stops and it returns that P is empty. Otherwise, we continue with the next step. If xt is in the polyhedron, then the algorithm stops, and it returns that P is non-empty. Note that in the very first iteration, xt is equal to x0, and in general it will be the center of the ellipsoid considered in the iteration. Let's then continue with the case where xt is not in P. This is, of course, the most interesting part of the main iteration. In this case, we have to define the new ellipsoid to be used in the next iteration. So if xt is not in P, we find a violated constraint. Formally, we find an index I such that AI transpose xt is strictly smaller than bi. Then we need to define the half space obtained by translating the corresponding inequality on xt. Algebraically, we let ht to be equal to the set of points x in Rn that satisfy AI transpose x greater than or equal to AI transpose xt. Then we find an ellipsoid ET plus 1 containing the half ellipsoid ET intersected HT, and we can do so by applying theorem 8.1. Finally, we increase our iteration counter by 1. We are now ready to show that the ellipsoid method is correct. Let P be a bounded polyhedron that is either empty or full dimensional, and for which the prior information x0, r, v, and capital V is available. Then the ellipsoid method decides correctly whether P is non-empty or not. Let's see a sketch of the proof of this theorem. The easy case is when one of the centers xt is in P, for some t strictly smaller than t star. Then the algorithm has found a vector in P, and so it correctly decides that P is non-empty. So now we need to assume that all the centers of the ellipsoids are not in P. The centers are x0, x1 until x t star minus 1. From theorem 8.1, we then obtain that P is contained in all the ellipsoids that we have considered. So P is a subset of Ek for every k from 0 to t star. Next, we wish to upper bound the ratio between the volume of the very last ellipsoid and the volume of the very first ellipsoid. We can compute this upper bound using recursively theorem 8.1. In fact, theorem 8.1 gives us an upper bound on the ratio of the volumes of two consecutive ellipsoids. So we break down our ratio as the product of ratios of volumes of consecutive ellipsoids. So we first consider the volume of ET star divided by the volume of ET star minus 1, then the volume of ET star minus 1 divided by the volume of ET star minus 2, and so on and so forth. At the very end, we consider the volume of E1 divided by the volume of E0. Of course, in this product, all the volumes simplify except for the volume of ET star and the volume of E0. We know from theorem 8.1 that each ratio is upper bounded by e to the minus 1 divided by 2n plus 1. So the product is upper bounded by e to the minus t star divided by 2n plus 1. We can now bring the volume of E0 to the right-hand side and obtain that the volume of ET star is strictly smaller than the volume of E0 times this exponential. This is exactly what we have written here. Now we know that the volume of E0 is at most a capital V, and we substitute T star with its definition, which is the ceiling of 2n plus 1 log of capital V over V. Now you can upper bound this quantity by essentially simplifying in the exponent 2n plus 1. So far we have obtained that the volume of ET star is upper bounded by capital V times e to the minus log of capital V over V. We can now get rid of the minus by flipping V with capital V. We obtain capital V e to the log V over capital V. Of course, e and log simplify, so we obtain capital V times V divided by capital V, and this is simply V. So we have obtained that the volume of ET star is at most V. Now, since P is contained in the last ellipsoid ET star, we have that the volume of P is at most the volume of ET star, and we have just shown that this is at most V. We have shown that in this case the volume of P is at most V. Now recall that by assumption our polyhedron P is either empty or it has volume strictly larger than V. Therefore, the only possibility is that P is empty. And this concludes the proof of theorem 8.2. In the previous video, we have already seen a visualization of the ellipsoid method in dimension 2. What I want to do now is to visualize the ellipsoid method in dimension 1. The reason is that I want to highlight how the ellipsoid method in dimension 1 closely resembles binary search, which is a basic technique to decide if intervals in the real line have a non-empty intersection or not. In this example, we consider the polyhedron P in R1, defined by the four inequalities x greater than or equal to 0, x greater than or equal to 1, x less than or equal to 2, and x less than or equal to 3. Below, we have a picture that represents these four inequalities. The first half line represents the points x greater than or equal to 0. The second half line represents the point that satisfies x greater than or equal to 1. The third half line corresponds to x less than or equal to 2, and the last half line corresponds to x less than or equal to 3. From the picture, it is clear that the polyhedron P consists of the segment between 1 and 2. Therefore, this polyhedron is non-empty. Now let's see how binary search is able to detect that. In our ellipsoid method, we start with an ellipsoid that is guaranteed to contain P. Ellipsoids in dimension 1 are simply segments. And the segment that is guaranteed to contain P is, for example, the segment between 0 and 5. Next, in the ellipsoid method, we look at the center of the ellipsoid. In dimension 1, this is simply the midpoint of the segment. In this example, it is the point 2.5. We check if this point is in P by checking all the constraints. And we realize that it violates the constraint x less than or equal to 2. Now, in the ellipsoid method, if we translate this inequality on the point 2.5, we obtain the inequality x less than or equal to 2.5. So the half ellipsoid containing P is the segment between 0 and 2.5. We now need to construct an ellipsoid that contains this half ellipsoid. Since we are in dimension 1, our new ellipsoid coincides with the previous half ellipsoid, and so it is equal to the segment between 0 and 2.5. In the next iteration of the ellipsoid method, we look again at the midpoint between 0 and 2.5. This is 1.25. We check if it is in the polyhedron, and in fact it is because it satisfies all the four inequalities. So the algorithm returns that P is non-empty, and it also returns the point 1.25, which is in P. Now that we've also understood how the ellipsoid method looks like in dimension 1, let's get back to our assumptions of boundedness and full dimensionality. Recall that in our development of the ellipsoid method so far, we have made the following two assumptions. First, that the polyhedron P is bounded, and second, that the polyhedron P is either empty or full dimensional. We also assumed to have in input the ball E0 containing P and the numbers V and capital V. The next thing that we want to do is to show that the ellipsoid method can be modified so that it works even if these assumptions are not satisfied. In particular, we will see how we can compute E0 and numbers V and capital V from the input system AX less than or equal to B. First, we discuss how we can relax assumption 1. So now we deal with polyhedra that are not necessarily bounded. The key in relaxing this assumption lies in lemma 8.2. Let's read the statement of this lemma. Let A be an m by n integer matrix and let B be a vector in Rm. Let U be the largest absolute value of the entries in A and B. Then every extreme point of the polyhedron P, defined by the system Ax greater than or equal to B, satisfies xj between minus nu to the n and nu to the n, and these inequalities hold for every j from 1 to n. I leave the proof of lemma 8.2 as an exercise for you. This is just an exercise of linear algebra. Everything you need to do is use the definition of basic feasible solution and then use Cramer's rule to obtain the bound. In particular, lemma 8.2 implies that all the extreme points of P are contained in the polytope PB. PB consists of all the points in our original polyhedron P that have all coordinates xj between minus nu to the n and nu to the n. Therefore, we have that P is non-empty if and only if PB is non-empty. Now our original problem was to detect if P is non-empty, and now equivalently, we only need to detect if PB is non-empty. But now we're happy because PB satisfies our assumption 1, since PB is bounded. Now let's stop for a minute and discuss a little bit more this if and only if. One direction is obvious. PB is a subset of P. Therefore, if PB is non-empty, then P is non-empty as well. Now the other implication from left to right is essentially proven by the argument that I just gave. Essentially, if P is non-empty, then look at one of its extreme points. From lemma 8.2, such an extreme point is also in PB, and so PB is non-empty. Of course, this is not a complete proof, because in particular I am assuming that P has extreme points. Now, what if P doesn't have any extreme points? In this case, this if and only if is still true, and I leave the proof as an exercise for you. As a hint, I suggest that, starting from P, you consider the 2 to the n polyhedra obtained by intersecting P with the 2 to the n different orthents. So we have shown that given a general polyhedron, we can reduce ourselves to consider a bounded polyhedron. However, we still need to determine our E0 and our capital V. To do so, we first observe that every vector in PB has components with absolute value at most n u to the n. Geometrically, this set is simply a hypercube, and it is a simple exercise to show that this cube is contained in the ellipsoid with center 0 and radius square root of n times n u to the n. Then we can also compute our value capital V by upper bounding the volume of E0. An upper bound is 2n nu to the n all to the power of n, which can also be written as 2n to the n times nu to the n square. So at this point, not only we have understood how to relax assumption 1, but we have also understood how we can compute E0 and capital V. In this way, we will not need to require E0 and capital V as part of the input of the algorithm. Next, we discuss assumption 2. This assumption states that the polyhedron P, if non-empty, has full dimension, or equivalently, it has positive volume. The first thing we need to understand is why we actually needed this assumption in our simplex method. This is because without this assumption, P could be non-empty and it could have volume equal to 0 at the same time. For example, this happens for all the polyhedra that have dimension lower than n, like a segment in R2. Now you see that if such a polyhedron is used as the input of our ellipsoid method, the algorithm could very well terminate after t star steps because it never found a point in the polyhedron. After these t star steps, then the algorithm decides incorrectly that P is empty. Let's visualize an example. Here our P is indeed a segment in R2. It is the set of points x1, x2 that satisfy x1 plus x2 equal to 1 and x1, x2 greater than or equal to 0. So it is the segment joining the point 0, 1 and the point 1, 0. Clearly the volume of P is 0, but P is non-empty. In particular, in this picture, I am visualizing the four inequalities that define P. We have x1 greater than or equal to 0, x2 greater than or equal to 0, x1 plus x2 greater than or equal to 1, and x1 plus x2 less than or equal to 1. The idea that allows us to reduce ourselves to the full dimensional case is to consider a small perturbation of our polyhedron. Essentially, we relax every inequality defining our polyhedron by some small epsilon. In our example, the inequality x1 plus x2 greater than or equal to 1 is replaced by x1 plus x2 greater than or equal to 1 minus epsilon. The inequality x1 plus x2 less than or equal to 1 is replaced by x1 plus x2 less than or equal to 1 plus epsilon. Finally, the inequalities x1 and x2 greater than or equal to 0 are replaced by x1 and x2 greater than or equal to minus epsilon. In general, the new polyhedron will be denoted by p epsilon. In our picture, essentially we translated by an epsilon each one of the four inequalities. The inequality x1 greater than or equal to 0 is translated a little bit to the left. The inequality x2 greater than or equal to 0 is translated a little bit downwards. The inequality x1 plus x2 greater than or equal to 1 is translated a little bit downwards, and the inequality x1 plus x2 less than or equal to 1 is translated a little bit upwards. So now essentially we opened up the feasible region. Originally it was just a segment, and now it is this gray region, which clearly is full dimensional. So now let's see this construction in a general way. In lemma 8.3, we consider our polyhedron P given by the set of points in Rn that satisfy Ax greater than or equal to B. Without loss of generality, we assume that A and B have integer entries, which are bounded in absolute value by capital U. We then define our epsilon using this formula over here, that is just a function of n and capital U. And then we use epsilon to define P epsilon as the set of points in Rn that satisfy Ax greater than or equal to B minus epsilon times the vector of all ones. The lemma then says that if P is empty, then P epsilon is empty as well. Furthermore, if P is non-empty, then P epsilon is full dimensional, and of course non-empty. We will not see the proof of this lemma, and if you're interested, please look at the book. However, let's see how we can use this lemma. Clearly, the lemma implies that P is non-empty if and only if P epsilon is non-empty. Our original problem was to understand if P is non-empty. Now, equivalently, we only need to understand if P epsilon is non-empty. The reason why we want to consider P epsilon instead of P is that now P epsilon satisfies assumption 2. It is either empty or full dimensional. So we've now understood how we can relax assumption 2. However, we still need to compute a positive number V that lower bounds the volume of P. This can be done using lemma 8.4. In this lemma, we consider a polyhedron P, which is the set of points x in Rn that satisfy Ax greater than or equal to B. We also assume that P is full dimensional and bounded, and that the entries of A and B are integer and have absolute value bounded by capital U. Then the volume of P is strictly larger than this number here. In particular, this is a positive number, which is a function of n and capital U. The proof of this lemma is actually pretty simple. Since P is full dimensional and bounded, there exist n plus 1 affinely independent extreme points of P. Everything you need to do is to compute the volume of their convex hull. And computing the volume is not too difficult because the convex hull is a simplex. So overall, this lemma 8.4 tells us that if P satisfies the assumptions of the lemma, then we can set V to be equal to this number over here. We're now ready to put all our ingredients together and discuss the complexity of the ellipsoid method. Our input is only a polyhedron P defined as the set of points x in Rn that satisfy Ax greater than or equal to B. So the matrix A and the vector B are given in input. They have integer entries and they have absolute value bounded by some capital U. Now the easy case is whenever the polyhedron P satisfies assumptions 1 and 2. Under these assumptions, we have shown already in theorem 8.2 that the ellipsoid method correctly decides whether P is empty or not in big O of n log capital V over V iterations. Now we also know that if assumptions 1 and 2 are satisfied, then E0, V and capital V, which are required for the execution of the algorithm, can be defined by the algorithm as follows. E0 is the ball with center 0 and radius square root of n and u to the n. The number V is equal to n to the minus n and u to the minus n square n plus 1. And finally, capital V is equal to 2n to the n and u to the n square. If we now substitute capital V and V in our number of iterations, we obtain that if assumptions 1 and 2 are satisfied, then the number of iterations of the ellipsoid method is big O of n to the 4 log nu. In particular, this number of iterations is polynomial in our input size, which is big O of nm log u. Let's now consider the general case. So we have an arbitrary polyhedron P. First, we reduce ourselves to the bounded case by creating the bounded polyhedron PB. At this point, PB satisfies assumption 1. Next, we perturb PB as in lemma 8.3, and so we form a new polyhedron PB epsilon. Now PB epsilon satisfies assumption 1 and assumption 2. We've already seen that P is non-empty if and only if PB is non-empty, if and only if PB epsilon is non-empty. So now, to understand if P is non-empty, we can instead analyze PB epsilon, which satisfies both of our assumptions. To understand the number of iterations of the ellipsoid method, we now need to construct E0, V and capital V, starting from our polyhedron PB epsilon. PB epsilon still lives in the space Rn, but now the absolute values of the coefficients in the inequalities will no longer be upper bounded by the original capital U, and so we need to figure out an upper bound on these absolute values. If you do so and then substitute V and capital V in the formula for the number of iterations, you will obtain that this number of iterations is big O of n to the 6 log nu. So the only difference with respect to the easier case is that we have n to the 6 instead of n to the 4. In any case, this number of iterations is polynomial in the size of the input. Now, to show that the ellipsoid method runs in polynomial time under the bit model, we also need to show that the number of arithmetic operations per iteration is polynomially bounded in n and log u. To prove this, there are two difficulties that we discuss next. The first difficulty involves the computation of the new ellipsoid. As we have seen in theorem 8.1, to calculate the center of the new ellipsoid, we need to calculate a square root. The problem is that we cannot always compute square roots, because a square root can be an irrational number, which cannot be written with a finite number of binary digits, and so it has essentially infinite size. Recall that in a polynomial time algorithm, every number that we compute must have a polynomial size. The idea here is to approximate this irrational number using an approximation of polynomial size. It can be shown that if we use this approximation, then the error that we make at each step of the computation will not lead to large inaccuracies in later stages of the computation. The next difficulty is in a way connected with the previous one, but it is a little bit more general. In fact, we need to show that all the numbers that we generate at every step of the computations have polynomial size. So we don't have a potential problem only when we compute the square root, but also when we recursively multiply numbers. In fact, by multiplying numbers recursively, potentially you might create numbers as large as 2 to the u. This would be a problem because the size of 2 to the u is big O of u, which is exponential in log u. Fortunately, both these difficulties can be solved, and they can also be solved in a fairly elegant way. Everything you need to do is to only use big O of n cube log u binary digits of precision for every number that you compute in the algorithm. Essentially, if the number that you compute has a larger size, then you take its closest approximation of size n cube log u. If you do so, it is obvious that all the numbers that you compute have polynomial size, and it can be shown that the ellipsoid method is still able to correctly decide whether P is empty or not in big O of n to the 6 log nu iterations. Admittedly, these results are very technical and difficult to prove, so we will not discuss any more details about them. In any case, this discussion leads to the following key theorem. The linear programming feasibility problem with integer data can be solved in polynomial time under the bit model using the ellipsoid method. With this theorem, we conclude our discussion of the ellipsoid method for the feasibility problem. In our next video, we will see how the ellipsoid method can also be used to solve linear programming optimization problems.